All right, so the last lecture for this chapter, chapter 16, is proofreading, and we're going to look at that, and we're going to look at telomeres and their issues. DNA is read, the polymerase comes through and starts adding to the 3' end. And what you need to know is going to happen is there's going to be issues, just like if you're typing. And what they've decided, what they figured out, is your initial pairing errors are 1 in 100,000. So that's a lot of mistakes, and those mistakes can actually cause issues. But what we want you to know is proofreading. So DNA polymerase can come back through and it can actually correct any issues. And so what it does is it goes through a second time and makes sure that all the matchings are correct. And if it's not, it will pull out and replace those issues. So it goes from 1 in 100,000 to 1 in 10 billion. And since we have 3 billion base pairs, that means that most of the DNA made, at least a good portion of it, is error-free. Okay. There's different types of proofreading. One is called mismatch repair. And that's when the enzymes go in and replace in an incorrectly paired nucleotide. Now, typically they're not sitting correctly, and so it will be taken out and replaced. There is also what we call nucleotide excision repair. These have nucleases in them. There's usually some kind of bump or that goes in there, and so instead of just having a one-letter replacement, this will be done where a huger section is replaced. And then again, ligase will come up and seal any of those attachments. All right, so that's proofreading. Now, there is also what we call an end replication problem. Again, I said several times, is nucleotides can only be added to the 3' end. On the leading strand, there's always going to be a gap, and that gap is where the primer is. Once that little primer is removed, we can't add nucleotides on that end. And the primers are about 5 nucleotides wrong. So every time that you replicate on the leading strand, you're going to be about 5 nucleotides shorter. And so every time your new DNA molecule is built, it's going to be a little bit shorter, which is going to cause a problem. So what happens is chromosomes have what's called telomeres. And these are things on the very ends of the chromosomes that are repetitive. There's a repetitive information there that is obviously not necessary for coding. And so what happens is they've got this built-in extra part. And in this picture, the stuff that's fluorescent is actually the telomere. So what can again, what happens is we just have this repetitive part where each time it's going to get a little bit shorter. There is actually an enzyme called telomerase that can actually rebuild that, but most cells do not use that. It's found in germline cells, things like stem cells, things like spermatocytes, things that are continuously producing cells. Unfortunately, it's also found in cancer cells. One of the thought processes is cells die is because they run out of DNA that's functional. That telomere disappears. So cells can only replicate a certain amount of time. So they thought, well, what if we give telomerase to a cell? And we actually have cells that do that. But also we found with a normal cell, you put telomerase in and you get what we call cancer cells that do not stop dividing. So we'll talk about that a bit later. All right, and then the last thing I wanted to talk about was chromosomes and chromatin. And so you're going to see these words, euchromatin and heterochromatin, and it really comes down to the way they're packed. So we're getting more and more information on whether they're loose or they're densely packed, and then what that means for cell division, things like that. Not going to go over too much now. But what you're going to find is this information will become important later when we do cell division, mitosis and meiosis.